3 days explaining flux. Right? And by the time I was done, I think I gave the most elegant argument for what flux was. Because, you know, it's just, yeah, it's a hard concept. But I spent 3 days on it. Worked out problems on flux, did everything. And then at the end of the third day, so I said, are there any questions? And I had this one student raise his hand and said, what is flux? I felt like saying, well, flux.
This is flux. That's funny.
Yeah, so nothing could be worse than that. You didn't get that, did you?
All of your classes.
Yeah, I think so. I got to hand it.
Gosh, what are these things? They're cool. And I like messing with
I don't know what it is.
or something. I don't know. It'd be cool if it's air on there.
You're right up to the president's office.
You're like, you suck.
Really here, there's no stat. It's for video.
Oh, is that what it is? Really?
That doesn't really work. So.
It doesn't work? That's right, because you're supposed to go be able to teach a class here and in Huntsville at the same time.
And that doesn't really work.
Doesn't really work.
It works in theory.
That would be cool. Both classes, both places.
Actually, we do it up and down in the state. We've got branch campuses over in the Shoals and over on Sand Mountain. And like advanced calculus is taught in the main classroom building in the teleconference room. And it's broadcast over to Shoals and over to Sand Mountain.
Does the instructor see the other class and
Mhm.
look their camera on them
Mhm.
and they can ask you questions and stuff?
I tried it with Mr. Drokels last semester.
That's pretty cool.
Didn't work.
We started that in high school.
Yeah, right.
I'll let you know later. I got a question. Yeah, no. What I have in my hands.
First class I'm in this morning, the roll takes 2 sheets. I'm just waiting for some people. What do you have? I have literature. I take it in 5 weeks because I really don't like it.
Do you guys as a teacher?
I have a lot. My teacher's pretty nice. Makes me interesting. So, makes me want to show up.
Thanks, Liz.
We're in the nose.
You know what song?
Anyway, I'm.
You know, I heard the study on CNN there that said teachers bet made less than 35,000. They got a house.
I'll make a lot more.
Sorry, I was
I got these things at that grocery store, and I'm sure you know what I'm talking about, like whenever you boil pasta, the microwave and stuff, it says put this much water in there, microwave it on, medium high, water warm. Then there's high altitudes, and it changed completely for high altitudes. Why is that? Why do you
Because
have to
there's
add
less-
3 more tablespoons of water?
There's less air pressure. So when you have less air pressure, it holds with less different amount of energy than higher air pressure. Sort of like how a piece of bake's different.
Yeah.
So, you know, I think at high altitude, you lower the baking.
Higher altitude, you have lower pressure, therefore you have a lower boiling point.
Yeah.
It'll change the boiling point.
Why would it change? Why would you have to add 3 more tablespoons of water then
You add 3 more tablespoons of water.
for high altitude?
Well, the noodles are going to absorb some of the water.
Well, obviously.
Maybe they absorb more water.
But the easy answer is just that it does change all the dynamics. So that's the easy cans because it covers everything. You have to change the pressure, you know, both within the cell itself, and then you also have to change the absorption, all that. I don't know the specifics.
All right, I'll take it.
I started thinking about this class, and no one's asked me what the tests are going to be like.
Well, I've had it twice already, so.
Well,
We got a car
I-
copy of
you're allowed a formula card. Or what do we get a carbon copy? Carbon copy? Only if you come up with the formula.
I got it. I look back at what I did last year, and I think it worked out pretty well. And what I did was, I basically took problems off of these problem sets. Some are off of these problem sets. Except for the matching page. It still was a matching page. And there were 2 multiple choice problems. Of course, those were off the problem sets. And then I had 6 out of 7 problems off the problem sets. But there's a lot of problems on these problem sets. All right? But theoretically then, if you did all the problem sets and you understood what was going on, then you'd be ready for the test. Was that one? And so it's very important that you understand all the problems of the problem set, right? And I know we went pretty fast in the last class. We gave you a lot of material in one class. So I thought today we'd work some problems and problem sets, and then I'd give you a shorter lecture than I did last time. Yes. Right. Yeah, lab reports are due the next lab class. Just like what we did before. Same format. It doesn't have it in here.
Yeah, that's why I didn't think I was like, there's no format, so maybe we don't do lab reports.
Was it not a lab syllabus?
No, there isn't.
Yeah, it's got the purpose, the body,
Right.
the very first sentence.
Oh.
The lab is,
It might not be at the first
I
page of the lab.
was looking
It
like
was
the
like
lab
the first
report
page
section.
in the actual book.
Yeah, it's the first page of the whole thing.
did you choose one of those? Yes.
I think so. Maybe not. Basically, they report
This is the third semester.
everything you do in lab, questions you answer, data you fill in, all that is your body of your lab. All right, so you're just gonna pull that out of the binder, and then you have to write a purpose page, which is a statement of your main objectives in that lab. What was the main thing that you wish to find out in that lab? And then the conclusion page has 4 things. You restate the purpose, you state the main data that pertains to that purpose, you state your percent error of your main data with theory, and then state 3 sources of error. Some of those sources become pretty magic, but state 3 sources of error, at least 3 sources of error. Right, so that would be what's in the conclusion. So you can write up your purpose page, write up your conclusion page, make sure you got all your data and questions answered, sandwich them together, staple them. That's your lab report. Except for 2 of them, I want the purpose and conclusion page type. Just to prove that you can do it. Sound good?
Fantastic.
If you want to see examples, we got examples upstairs.
Okay, so, what about chapter 19? Any questions from that chapter? I forget which ones we've done.
8, 9,
6, 8, and 9 we've done.
16, 17.
We really have done pretty good treat tonight. We look at 18. So the square plate has an area of 29 square centimeters at 20 degrees centigrade. It will be used in a low temperature experiment at temperature equal to 10 Kelvin, where it must have an area of 28 square centimeters. What area must be removed from the plate at 20 degrees centigrade for it to have the correct area at 10 Kelvin? Coefficient of linear expansion is 10 times 10 to the minus 6 per degree Celsius, per degree centigrade. All right, so we have a square plate. Its area is 29 square centimeters at 20 degrees centigrade. Kelvin. We wanted to have an area of 28 square centimeters at 10 Kelvin. So we want area 2, area 1. 28 square centimeters at T1 equal to 10 Kelvin. How can I ensure that I can have 28 square centimeters at 10 Kelvin when I cool this plate down? In other words, the question is, ultimately the question is, how much of this do I have to remove so that when I cool it down to 10 Kelvin, I have 28 square centimeters? Jason?
This is what I would do. To start off the problem, I wouldn't even worry about the area that you start off with. Just don't even worry about it. So you know the final, and you know its initial temperature. Using your using the coefficient, figure out the area, using your end result, figure out the area that it would need to begin with, and then compare the two, your given area and the area that you calculate it needs to be, and find the difference.
Everybody follow that? That sounds pretty good to me. So the idea is this. Since we want 28 square centimeters at 10 degrees Kelvin, let's treat that like our initial temperature and warm it up to 293 Kelvin and see how much it expands. All right? And see what that total size is when it expands, because that's the size we want to start with when we cool it down. And then the difference between that and 29 square centimeters is how much you need to remove. Okay. So, let's do that.
How do you do this?
Oh, basically the same thing.
Yeah.
A1 is our original size, 28 square centimeters. And so then we'd say that our, we're given that the linear coefficient was 10 times 10 to the minus 6. Per degrees Celsius. Our initial temperature is 10 Kelvin. Our final temperature is 293 Kelvin. We're actually dealing with an area, not a linear piece. So the coefficient for an area, which we'll call gamma, is twice this. That's 20 times 10 to the minus 6. What else do I need to know? I think that's it. So we'd say that our final area, will be our initial area times 1 plus gamma delta T. In other words, it's going to be the initial area plus the area that changed, 1 plus gamma delta T. This would be 28 times 1 plus 20 times 10 to the minus 6. And our change in temperature is going to be 293 minus 10. We put all that in there. I get 28.159 square centimeters. So that would be, if we had expanded from 28 square centimeters up to room temperature, it's now 28.159 square centimeters, so that's what we would have wanted to start with. We're going to start with this and cool it down to 10K, we'll end up at 28 square centimeters. So we need to remove the difference between that. We need to remove an area equal to 29 minus 28.159, which would be 0.841 square centimeters. Neat. So what else look pretty challenging?
Maybe 22.
Let's take a look at 22. That looks, I was just looking at that when we mentioned that.
Telekinesis.
Suppose the ends of a 30-meter long steel beam are rigidly clamped at 0 degrees centigrade to prevent expansion. The beam has a cross-section of 30 square centimeters. What force against the clamps does the beam exert when it's heated to 40 degrees centigrade? I go back between centigrade and Celsius. The linear coefficient of steel is 1.1 times 10 minus 5 per degree centigrade, and the Young's modulus for steel is 20 times 10 to the 10 newtons per meter. Okay, so what do we got this beam of steel. And the original length is given as 30 meters. The original temperature is 0 degrees centigrade. We're going to heat to 40 degrees centigrade, so we're going to have a change in temperature, 40 minus 0, or 40 degrees centigrade. Cross-sectional area is 30 square centimeters. So this area here is called area naught. 30 square centimeters, and what else? Coefficient, linear coefficient for steel is 1.1, 10 to the minus 5 per degree centigrade. And Young's modulus for steel, oh, this is for steel, it's 20 times 10 to the 10 Pascals. Newtons per meter squared. We want to find the force that the clamps, we're going to clamp this on both sides. Then we're going to heat it up by 40 degrees, so it's going to expand. It's going to start pushing on those clamps. And ultimately, we want to find what that force is that's pushing on the ends. And we need to use Young's modulus to do that. How do we do that?
Well, you're gonna need to find the change in length.
Okay, so let's do that first. Let's just get that done. The change in length is going to equal alpha times original length times the change in temperature. All right? So that's going to be 1.1 times 10 to the minus 5 times 30 meters times 40 degrees centigrade. What is that?
Oh wait, no, that's wrong. I'm there, that's. Yeah, 0.01.
I got 0.0132.
Yeah.
Okay. What's next? Do you remember that chapter 12 stuff with Young's modulus?
I remember Young's modulus and the other two, but I don't remember the formula for the last one.
Young's modulus is the stress over the strain. Stress over the strain. I don't know if that helps. What was the stress? Remember? We didn't spend a whole lot of time on it, but we just kind of introduced the formula. If you had a stress on something, it's actually really the pressure that you would exert in a mechanical sense. So it's really force per area. And what's the strain?
Is that the pushback?
Yeah, but it's a unitless quantity that relates how much something changed to the original amount. So it's the change in length over the original length in this case. So,
And then there's also a change in volume
over the original volume,
that would be what, beta?
that was beta, which was,
Volume.
or that's related to beta, which was volume strain,
Yeah.
which goes into the bulk modulus.
Yeah, that was what I called.
But we're doing the Young's modulus. Let's solve this for that force. Right? So let's multiply both sides by delta L over L naught. And multiply both sides by the area. So the force is going to equal Young's modulus times the change in length times the area over the original length. So that's going to equal 20 times 10 to the 10. Change in length, we just figured out 0.0132. The original area, I guess I could call it A naught, but let's write this as 30 times times 10 to the minus 4 square meter. Just be consistent. And the original length was 30 meters. So hopefully, it will give us our answer. I got 2.64 times 10 to the 5 minutes. $264,000 minutes. Probably not a good idea to originally clamp a steel beam and then heat it up. Give it some space to expand into. At least that would be 1.32 centimeters. So just give it a couple centimeters so it can expand.
Oh, it's gonna expand, whether you want it to. But that was voice.
Yeah, basically, yeah, you're right. Depends on whether you want it to expand into open space or into something else.
Should we put the formula for things like this on our cards? It's like, is this a problem you would get?
Essentially an extra credit problem, read point.
I do a lot of
Yeah, I'm giving you a break in a sense by saying I'm just going to pull problems from these problem sets. So
Yes.
with that premise, you got to be ready for anything.
Yes.
So yes, I'll be ready, even though this is just one problem. Anything else from chapter 9 that looks like we should be doing it? Did I do number 11? Nice, straightforward one.
No, yeah.
An auditorium has a volume of 6 times 10 to the 3 cubic meters. How many molecules of air are needed to fill the auditorium at standard temperature and pressure? What is standard temperature and pressure?
1 atmosphere at 0 degrees Celsius.
Okay, 1 atmosphere and 0 degrees Celsius. So pressure, 1 atmosphere. What is 1 atmosphere in pascals?
7.
Pascals being newtons per meter squared.
Like that.
So, no, that was the gas constant.
That was like 1.67, so.
Wow. All right, you're gonna need a big card.
Yeah,
All
yeah.
right.
I was gonna ask if it's doubled since last semester.
You're gonna need to know that. All right, that'd be the conversion from atmosphere to pascals. 1.013 times 10 to the 5 newtons per meter squared. Volume, let's see, it's a temperature, standard temperature, 0 degrees centigrade of Celsius, which would be 273 Kelvin. Or you could put 1.15 on there. But if we use these units, which is SI units, then the gas constant is 8.32. Units, right? All right, so how many molecules of air are needed to fill an auditorium at standard temperature and pressure? We have a volume, 6,000 cubic meters. And so we're going to use ideal gas law.
PV equals nRT, and we're solving for N.
Exactly. PV equals nRT, we're going to solve for N, the number of moles of gas that we need first. So number of moles will equal PV over RT. All these units are in the SI system. So we have 1 atmosphere, 1.013 times 10 to the 5 newtons per meter squared times 6,000 meters cubed over 8.32 over 273 Kelvin. And I guess when I plugged it in here, I used 273.15, but I come up with 2.67 times 10 to the 5 moles.
And we need to multiply that by Avogadro's number, right?
Exactly.
Which is 6.022 times 10 to the 23.
Correct. That's the number of moles. We need to convert this using Avogadro's number to get the number of particles that would be. In other words, the number of particles will equal the number of moles times Avogadro's number. Basically a conversion. Avogadro's number is the number of particles per mole. So this would be 2.67 times 10 to the 5. Jason said Avogadro's number is 6.022 times 10 to the 23 particles per mole. And if we make that product, I get 1.61 times 10 to the 29 molecules. So that's how many molecules of air would be needed to fill that auditorium. 1.67 times 29. Okay. Oh, you used the other way? Was it better? So you use liters and atmospheres? It worked? Either way. Either way, any way that works. So you would have to convert that volume into liters. Anything else on chapter 19? Chapter 20. Um, 15 would be better after we introduce what I'm going to introduce today. So that would be the subject of the first law for today. And there's a bunch of stuff that we still haven't introduced yet for this chapter. Including number 11. 11 has to do with Stefan's law. We haven't introduced that yet. So really, so far, we've introduced material to deal with calorimetry, which would take us to problem number 7. And section on conduction, which we have not looked over yet. We haven't done Stefan's law. After today, then from 13 on would be fair game.
Can we do like two?
Do like two and then look at today's stuff and then maybe do a couple more.
Yeah.
I think that's a good idea. Do you know which two you might want to suggest? We already did a few.
Four, you want to do four?
Okay, I didn't do four before.
Just, I haven't looked at it since Monday, so.
Pam? '24. 300 gram glass thermometer, initially at 25 degrees Celsius, put into a 200 cubic centimeters hot water at 95 degrees Celsius. Find the final temperature in degrees Celsius of the thermometer, assuming no heat flows to the surroundings. Specific heat of glass is 0.2 calories per gram per degree Celsius. All right, so we have some water, and it's 200 cubic centimeters of water. So, since we're given the mass of the thermometer, let's do that first. Thermometer, mass of the thermometer is 300 grams. And the temperature of the thermometer is 25 degrees Celsius. Should I use 25 degrees Celsius? Let's keep it like that for the moment, and I'll explain why in a moment. The hot water is at 95 degrees Celsius. This is the temperature of the thermometer. So the temperature of the water, 95 degrees Celsius. And we're told that we have 200 cubic centimeters, or 200 milliliters, of hot water. How does that translate to mass? Assuming that it's pure water.
Water weighs, is it 1 kilogram a liter?
Yes.
Okay. Water weighs 1 kilogram
Or has a mass of 1 kilogram
per liter.
per liter.
So 200 centimeters cubed, that's equal to 0.2 liters. So 0.2 kilograms.
Exactly. In other words, by definition, a cubic centimeter of water, pure water, is a gram. All right? A milliliter of water is a gram by definition. So if we have 200 cubic centimeters of water, we have 200 grams, or 0.2 kilograms. So the mass of the water is, let's leave it in grams because we're given our specific heats in terms of grams. 200 grams. All right, so we're going to add a cold thermometer to the hot water, and they will equilibrate. In other words, the hot water will lose some energy by heat, will lose heat, and the thermometer will gain heat. And the amount the hot water loses is the amount the thermometer will gain. We're assuming it's an isolated system, so there's no heat flow to the surroundings. That's in the problem. So, and we're also given the specific heat of the thermometer in 0.2 calories per gram per degree Celsius. 186 joules per,
Kilogram. Centigrade, whatever.
what is it in, calories?
That's why we left it in degrees centigrade, because we have degrees centigrade in the specific heat thermometer. Oh,
Well,
is it? No?
yes and no.
No.
I'm going to explain that in a moment. But let's finish this thought. What is the specific heat of water in terms of calories per gram per degree Celsius? One. By definition. So specific heat of water is 1 calorie per gram per degree Celsius. Now, if you convert that, then you multiply by the 4.186. Actually, 4,186, because normally if you do it the other way, you're going to have joules per kilogram per degree Celsius or Kelvin. Get all that out. Okay, so the way I would do this, I would say the heat loss by the water will equal the heat gain by the thermometer. Right? It's an isolated system. Whatever's lost by one will be whatever's gained by the other. So I can write this and say that the heat loss by the water will equal the heat gain by the thermometer. Heat being the mass times the specific heat times the change in temperature of that object. All right? When I look at it this way, when I'm going to equate the heat loss to the heat gain, these delta T's will be positive quantities. Right? So that I can equalize those on both sides. And for them to be positive quantities, for the water, this would be its initial temperature minus the final equilibrium temperature will be its change in temperature. So if it's change in temperature, which will be Celsius minus Celsius, that will be the same whether it's in the Kelvin or Celsius scale. So it doesn't matter whether we convert them in this case. If you're dealing with changes in temperature, you don't need to convert to Kelvin because it'll still be the same amount. Okay. And then over here, the thermometer is cold and it's going to get hot, so this change in temperature will be its final temperature minus initial temperature. So let's write this like this. Mass of the water, specific heat of water, times 95 minus the final equilibrium temperature will equal the mass of the thermometer times the specific heat of the thermometer times the final temperature minus its initial temperature, 25. Solve for T. Mass of the water is 300 grams. Specific heat of water is 1 calorie per gram per degree Celsius times 95 minus T equals the mass of the thermometer, which was 300 grams. The specific heat of the thermometer is 0.2 calories per gram per degree Celsius times temperature minus 25. This was 200. Right? Let's get rid of 100 on both sides. Sorry, Michael.
It's
Go all the way
okay.
over here. So at this point, I've got 2 times 95 minus equals 0.6 times T minus 25. Right? 2.6T minus 15. So I have 205 equals 2.6T. Or T will equal 205 divided by 2.6. That's what I added. I get 78.9. Since everything was done in degrees Celsius, that would be in degrees Celsius. That'd be the final equilibrium temperature of the system. What do you think about that? I definitely would like you to be able to do calorimetry problems like that. Well, the final temperature. So heat loss from one equals heat gained by the other.
So simply by measuring the temperature of a body of water, you've changed it beyond what you thought you would do.
Yeah,
Simply because of the heat transfer.
right. Now, in this particular case, that's a heavy thermometer compared to how much water you're trying to measure. In fact, the thermometer had more mass than the water. So, yeah, it's going to change the system. Let's try another calorimetry problem. Which ones on this first page have I done? You know? Nick? Just keep track of that. I didn't do anything else on this first page?
I don't think we've even gotten to chapter 20 yet.
I don't have any.
Oh, it's the first one we done?
Down from chapter
Last
20.
class you said go in and take some more, I think we'll get some next class.
Cool. All right.
Yeah, I don't know, Danny.
Let's try another one. Let's look at number 3. This is a 5 kilogram piece of lead, specific heat of 0.03 calories per gram per degree Celsius, has a temperature of 80 degrees Celsius, is added to 500 grams of water, having a temperature of 20 degrees Celsius. What's the final equilibrium temperature in degrees Celsius of the system? We have a piece of lead. Mass of the lead is 5 kilograms. So we could say it's 5,000 grams. It has a specific heat. It's mass of the lead. 0.03 calories per gram per degree Celsius. And the temperature is 80 degrees Celsius. That's for the lead. And we have the water. Mass of the water is 500 grams. Specific heat of water is 1. 1 calorie per gram per degree Celsius. And the temperature of this water is 20 degrees Celsius. If you really wanted to be safe, you would change those temperatures to Kelvin. And then you'd always be safe because we're going to do a lot of problems where you're going to have to do that. These calorimetry problems, it's not necessary because we're dealing with changes in temperature. And so we can get away with it. So we're going to add the hot lead to the water. Water's gonna heat up, the lead's gonna cool down, they'll reach some equilibrium temperature where they're at the same temperature. So we'll say that the heat lost by the lead would be the heat gain by the water. That's one way to think about it. So I'll say that the mass of the lead times the specific heat of lead times its change in temperature should equal the mass of the water times the specific heat of water times its change in temperature. Mass of the lead is 5 kilograms per 5,000 grams. Specific heat of the lead is 0.03. The change in temperature for the lead is going to start at 80 degrees Celsius and then go down to some final temperature. We don't know what that is, so this will be 80 minus T. That should equal the mass of the water, which is 500, times the specific heat of water, which is 1, times the change in temperature of the water, which will be
T minus 20.
T minus 20 Kelvin. There we have it. Solve that for T.
They just lost one.
Really?
They put the Japanese, what is it called? Koji, I don't know what it's called. They put the Japanese part of it in the States.
Oh, good.
Yesterday.
Was it yesterday?
It fixed the total. Yeah, the total
The
cost
Russian
been
plane
leaks, so
popped
that
in.
happened. But you told
Oh, the
They
Russian
actually had to
toilet.
take stuff off the
Yeah.
shuttle.
They put, no, the Russian
Because the
toilet,
Russian
they put
toilet didn't work right?
Exactly.
in- That was the third one they replaced.
It's the number 2 part that didn't work right. Number 1 part still worked. Well, I was just saying
Was
what
it
part.
built for the northern hemisphere or the southern hemisphere?
See, I didn't know that part of it.
I watch that channel sometimes.
I'm glad I missed that news story. Let's take 100 on both sides. 50, actually, I probably should have left it in there. 50 times 0.03.
150. Wait,
Point
oh,
five.
you
Or 1.5. 80 minus T. And over here, we just have 5. T minus 20. That's going to be equal to 5T minus 100. 0.15 times 80.
One,
It was 1.5.
1.5 times 80?
yeah.
Okay. So that'll be 120. Minus 1.5 times T equals 5T minus 100. So add 100 to both sides. So you have 220 equals 6.5T. T is equal to 33, more rounded, 33.9. So that'll be the final temperature, 33.9 degrees Celsius. You like these? Good. Like I said, I like them too, so very, very likely that you might see one of these on the test.
It'd be nice if we saw like 6 on the test.
I think if you look at it this way, the heat loss equals heat gain, it's easier to do. If you don't look at it that way, these problems can be pretty hard, actually. All right, you ready for something new or different?
I had a nickel every time I heard that phrase.
I know, I need to come up with something else, but
You ready for
that would be really Could be. Yeah, yeah, when on one of the tests, I was given in physics 1, I forget if it was Michael or
Marty.
Marty. Marty was goofing around with cameras, and he had that camera, and he had it focusing on one student. I could actually see the paper the student was writing. The focus was so good, and he put it up on the monitor back there. So I could just, oh, okay. So remember that. I can see whether you're cheating or not.
If you can read my writing, I am impressed.
Yeah.
Well, I'll eventually have to read it when I look at your test.
Yeah, well, I mean, if you're watching it on camera, you know,
No, that was.
How about you not look at somebody else? You're doing that.
The first law of thermodynamics. Basically, it's a statement of conservation of energy. I state that you're not going to change the energy of a system unless you add something to it. That's basically what it's saying. So if you didn't add anything to it, then the energy of that system will remain the same. So we're going to say that the change in internal energy, which I'll state it like this, change in energy internal, is equal to the heat added to that system as named by Q, plus the work done on that system as named by W. In other words, the way that we're going to state it, stated in different ways at different places. But the way we're going to state it is, if you had a system, its energy would change if you add heat to it or if you do work on it. And if you do either one of those things, the energy will go up. All right? If the heat that you add to the system is actually negative, so that there's actually heat going out of the system, or if you do work by the system, so that it's doing work, so it's losing energy, then in either of those cases, the internal energy of the system will go down. Let me restate that. That's the first law of thermodynamics. We're saying that the change in internal energy of a system is equal to the heat added to that system, which could be negative, plus the work done on that system, which could be negative as well. All right? Yes?
Change the E's for it, you get it right.
What's that?
Change in E, internal energy.
Is
You're not gonna classify that. But you can classify that into, gas turbulation.
now I'm going to use this. And later on, we're going to have entropy, which will be gas. And we won't define entropy. We'll use this. In some texts, they use U. So you're used to it. And in fact, you might see some typos in my notes where U kind of creeps in there, and I haven't changed it yet. All right, with this statement, we need to define a few things. We define what we call an isolated system as one that does not interact with its surroundings. So if a system is isolated, there can be no energy transfer by heat. So you can't increase the internal energy by adding heat or subtracting heat. And if the system is isolated, it can't do any work, and there can be no work done on it. It's totally isolated from the surroundings. If that were the case, then the heat added, the work done on the system will both be zero, and by the first law, the internal energy would be, the change in internal energy would be zero. Meaning, whatever internal energy it has would remain there. So the internal energy of an isolated system will remain constant. It won't change. Yes?
By heat, do you just mean like thermal heat, or
Yes.
do you mean like also, because it could release like light, couldn't it?
It could. It could. We're talking totally thermodynamics here.
Oh,
So radiation will come later.
okay.
A cyclic process. A cyclic process, by definition, is one that starts and ends in the same state. Hence, if it has some kind of internal energy to begin with, and it goes through a cyclic process, maybe you add energy in the form of heat, and you do some work or something along the way, and it goes through some cycle, but eventually comes back to the original conditions of, say, pressure, volume, and temperature. Then, actually, the main thing would be temperature. Then the change in internal energy would be zero. Process would not be isolated, but, and you could have heat added and work done. And on a PV diagram, a cyclic process would be a closed curve. So you could start at some point on a PV diagram that we introduced last time, and you would follow along to different conditions, but eventually you come back to your original state. So it's a closed curve. Hence, the internal energy must be zero. The change in internal energy must be zero because internal energy is a state variable, and we return back to the start. So if the internal energy, the change in internal energy is zero, and by the first law, that means that the heat added along the cyclic process should be equal to the negative of the work done on that system. So just by the first law, 0 is equal to Q plus W, and Q is going to equal a negative W. So the heat added to a system is equal to the negative work done on that system for a cyclic process. And I always think that the work done on a system is a negative of the work done by the system, because unfortunately, in the problems, there are some that use work done on the system and some that state the problem as work done by the system. Anytime you're going to do work on a system, you're going to, well, we'll talk about this later, but you're going to compress it, and you'll add energy to that system by doing work on the system. Work by the system would be generally some kind of expansion. On a PV diagram, the net work would equal the area enclosed going counterclockwise on a PV diagram. So if you had a cyclic process and you went from one point back to that same point, if you found the area enclosed by that process and you're proceeding counterclockwise in that process, then the work, that would be the work done, the area enclosed. If you go the opposite direction, you go clockwise on a PV diagram for a cyclic process, that would give you the net heat added to that system, the area of that. Here's an example. Here's my PV diagram. We're at pressure on this, on the Y scale, volume on the X scale. If I were to go counterclockwise on this, let's say if I went from B to A, I would be compressing the gas. I'd be going from a larger volume to a smaller volume. Hence, I'd be doing work on the gas. So that would be positive work done on that gas. Correct? If I went from A to D, the volume wouldn't change. So I'd be doing no work on the gas in that sense, because the volume of the gas doesn't change. Even though the pressure is going down, you can't do work unless you change the volume of the gas. If I went from D to C, the gas would actually be doing work. The gas would be expanding as it goes from a smaller volume to a bigger volume. So the work done on the gas would be negative. So the amount of work would be the negative, that area, as we proceed from D to C. And as I go from C to B, there'd be no work done because I'm at constant volume. So the work done would be the area enclosed by that little rectangle, because I did all this work done by the big rectangle first, did 0, and then I subtracted the work done by the little rectangle, and then I did 0. So in In the cyclic process, it's just the area enclosed as they go counterclockwise. And then the heat done would be if I went the opposite direction. And heat added is a negative of that. What do you think?
I understand a lot better than the other day.
Good. Because we're going to introduce this today, and we probably won't do, we'll use it in a cursory way on the problems in this chapter, but in the next chapter, it's going to come back again, and then we'll really use these diagrams a lot in chapter 21. Let's try an example here. The quantity of a monatomic ideal gas undergoes a process in which both its pressure and volume are doubled. What is the heat absorbed by the gas during this process? Now we're going to use something we're going to introduce later, but for a monatomic gas, the energy is 3/2 the pressure times the volume at any particular point. So that will be the internal energy. So what we're going to do is we're going to start at some volume and some pressure, which I'm going to call point A. We're going to increase the volume to twice as much. We're going to increase the pressure to twice as much. So this gas is going to proceed along this line here from A to B. Since the gas is expanding, will the work done on the gas be positive or negative?
Negative.
It would be negative. Very good. The question is, what's the heat absorbed by the gas? But we can find the work done, and we can find the change in internal energy, find the heat from the first law. In other words, the initial internal energy, by definition, is 3/2 the initial pressure times the initial volume. The final internal energy will be 3/2 the final pressure times the final volume. Well, the final pressure is twice the initial pressure, and the final volume is twice the initial volume. So the final energy of this system will be 3/2 times 4, or 6 times the initial pressure times the initial volume. So our change in internal energy will be our final internal energy minus our initial internal energy. 6 minus 3/2 will give us 9/2 initial pressure, initial volume. All right, so that's our change in internal energy. That will go on the left-hand side of the first law. Let's figure out the work done on this gas. You just stated that should be negative because it's expanding. The work done is the area underneath this graph, at least in magnitude. So, what is the area underneath that graph, the negative area underneath that graph? Well, that's going to be the area of this rectangle here, plus the area of this triangle. So that's going to be, this rectangle here is a rectangle that is P naught on one side, B naught on the other side. So it's just P naught times B naught. And the area of this triangle is going to be 1/2 base times the height, 1/2 P naught, B naught. So we'll have a negative 3/2 P naught, B naught is the work done on this gas. Good? We want to find the heat added to this system, and we know by the first law, the change in internal energy equals the heat added to the system plus the work done on the system, on the gas in this case. So, solving for the heat added to the system, that should equal the change in internal energy minus the work done on the system. That would be 9/2 P naught B naught minus a negative 3/2 P naught B naught. So this minus minus would be plus. And we'll get 12/2 or 6 P naught B naught. What do you think? Let's try another example. Take a look at this problem. gas is compressed at constant pressure of 0.3 atmospheres from a volume of 8 liters to 3 liters. In the process, 400 joules of heat energy flows out of the gas. Question is, what is the work done on the gas? All right, so here's our process. We're going to go from point A to point B on this PV diagram. We're going to start at 8 liters and go down to 3 liters, and we're going to do it at constant pressure. So basically, to find the work done, we want to find the area underneath this graph. Will give us the work done. Will that work, in terms of the first law, will that work be positive or negative?
Positive.
It'll be positive work because it's going backwards that way, counterclockwise if you think of it. And we're doing work on the gas. We're compressing the gas. Very good. So that'll be a positive quantity. In general, the work equals negative pressure times a change in volume. That'll be a negative 0.3 atmospheres, which I can convert to pascals by multiplying atmospheres by 1.013 times 10 to the 5. 3 final volume minus initial volume, 3 minus 8 liters. I'm going to convert that to cubic meters by multiplying by 10 to the minus 3. So I'm going to end up with SI units. And that gives me 151.9 joules. Newton meters. Positive. Right, so far so good. In the problem, we're also told that 400 joules of heat energy flows out of the gas. As I quantify Q, which is the heat that flows into the system, right? How would I quantify Q? Q would be negative because
The gas is in essence, it's heating up. It's compressing. So it's releasing the energy.
you're thinking too hard because you're considering the work at the same time. Let's not even worry about the work on this part of the question. We're just told that 400 joules goes out of the gas. So since it's going out and not in, it's negative. So it'll be negative 400. So the question is now maybe we can add the two. What is the change in internal energy? The first law, change in internal energy is the heat that flows into the system plus the work done on the system. We figured out the work done. We just said that the heat flowing into the system will be a negative 400. Negative 400 plus 151.9 joules, negative 248 joules will be our change in internal energy. Yes.
Where did the 140 material?
It's a constant.
That's that constant that we mentioned.
Oh,
You
okay.
probably are going to want on your formula card.
Okay.
That's that converts atmosphere to newtons per meter squared. Let's try one more. Problem 26. So the gas is taken through, probably in your book, not in your problem set. The gas is taken through a cyclic process described by the figure A, B, and C. Find the net heat transfer to the system during one complete cycle. Now, if it's a cyclic process, then we're going to end up back where we started. And if we went from A to B to C, we're going clockwise on a cyclic process. For a cyclic process, for the work to be positive, we have to go counterclockwise. So if we go clockwise, then the work done enclosed will have magnitude enclosed by the area. Is that right? The area enclosed by the cycle will be the magnitude of the work done. If we're going clockwise, will that work be positive or negative? Negative. One way to think of it is this. going from A to B, we're expanding, all right? We're expanding to a larger volume, and the magnitude of the work done would be the area underneath that trapezoid or the triangle plus a rectangle. By expanding, that would be negative work, because the work done on the gas would be negative. The work done by the gas would be positive. And when from B to C, there's no change in volume, so no work done. From C to A, we're compressing the gas, and we're doing work on the gas, and the magnitude of that work would be the area of this little rectangle. So we have a lot of negative work for this big object, and then we have this positive work for this little rectangle. If we subtract that little rectangle from the larger area, we end up with the area of that triangle, which is the enclosed area, and that would be negative work. Sound good? So let's find the area of that triangle. 1/2 the base times the height. I have 1/2 the base, which is going to be, well, I did the height first, 8 minus 2. And then I converted that as kilopascals. That's 10 to the 3 pascals. And then for the base, I have 10 minus 6, and that's already in cubic meters. That gives me a negative 1.2 times 10 to the 4 joules. That would be the work done on this gas. Change in internal energy of a cyclic process is 0 because we come back to the original state. So that means by the first law that the heat added is equal to the negative of the work done on the system. If the work done on this system was a negative 1.2, the heat added is negative of that. A negative gives us a positive 1.2 times 10 to the 4 joules. So the heat added to this system is 1.2 times 10 to the 4 joules. The hardest part of these kinds of problems is just imagining what's going on. Right? The mathematics is not hard. Just trying to figure out how the exchanges are taking place, what's happening. If we were to reverse the direction, both of these quantities would be opposite in sign. So if we were to go from A to C to B, and then back from B to A, the work would be positive, the heat added would be negative. The change in internal energy would be 0. So far, so good. Let's try this. 2 cubic centimeters of water are boiled. I'll probably put is boiled because I could just fit that line just barely on that with that font size. Is boiled at atmospheric pressure to become 3,342 cubic centimeters of steam, also at atmospheric pressure. Calculate the work done on the gas during this process. Okay, so I'm going to take 2 milliliters of water. I'm going to boil it. Boil it all into steam. In doing so, and we're going to say we're going to do this all at atmospheric pressure. So we're going through a phase change. So we're going to, that's one thing that's going on. So water's going to change from liquid to gas. But also, that water's expanding from whatever size it has as a liquid to whatever size it has as a gas. And so there's being work done by the water. I can say it like this. The work done is equal to the negative pressure times the change in volume of the substance. This is called isobaric because we're in a constant pressure. More on that later. But the term for constant pressure process like this is isobaric. Iso means same, baric meaning pressure. So we have a negative 1 atmosphere, which would be 1.013 times 10 to the 5 pascals. Our change in volume, our final volume, is 3,342 cubic centimeters. Our initial volume was 2 cubic centimeters for the water. Convert that to cubic meters by multiplying by 10 to the minus 6. And I get that the work done on this gas was a negative 338 joules. Why was it negative? Because it expanded. So it expands and the process is actually doing work. Right? So the work done on the process will be negative. Find the amount of heat added to the water to accomplish this process. The heat added will be the heat needed to go through the phase change from liquid to gas. Last time we said that's the heat for the vaporization of the liquid. So that would be the mass times latent heat of vaporization for water. That's 0.002 kilograms times 2.26 times 10 to the 6 joules per kilogram. So that would be 4.52 times 10 to the 3 joules. We need for the heat added to do the phase change. What's the change in internal energy? Well, by the first law, the change in internal energy is equal to the heat added plus the work done on the system. Heat added is 4.52 times 10 to the 3. The work done on the system is a negative 338 joules. So 4,520 minus 338. Our change in internal energy for this system is 4,182. I think kind of the rest of this lecture is kind of just defining some things, some concepts. Let's take a look at that. Say the energy transfer Q into or out of the system depends on the process. Any type of transfer you have depends on the process because it's not a state variable; it's a transfer variable. So how we get from one state to the next state is important. Here's an example. Here's a heat transfer. In this case, I think what we're going to do is we have a gas that initially is at this position. We have a piston here. We're going to grab that piston. We're going to pull it up and allow the gas to expand. So the piston is pushed upward or pulled upward, and in a sense, the gas is doing work on that piston. Helping move that piston. So the work on the gas is negative because the gas is doing work. We're going to say this energy reservoir here, which is connected to this gas, so it's not an isolated system. This energy reservoir is so vast that as it adds heat to this gas, the temperature of the reservoir itself is not going to change. It's a very vast reservoir at constant temperature. So it can easily give up some heat without changing its temperature itself. If we maintain the gas at that same temperature, so this is adding heat to maintain the gas at the same temperature, then heat must flow into this gas. So this gas is doing work, so the net work on the gas is negative. And to maintain the internal energy to be the same, so no change in internal energy, we must have a positive amount of heat going into this gas to offset the work done. All right, so that's one example. Contrast that with this example. We have an isolated system. We have a gas at the same temperature as we had before and the same volume as we had before. And we have some kind of membrane here, which we're going to eliminate real quickly. I don't know how we're going to do that. Maybe pull it out or just let it vaporize. It's another. So we're going to remove that membrane, and then we're going to take that gas, which is initially at temperature T sub I, and let it expand into the other volume. This gas has the same initial volume and pressure as the previous example. And the final state is going to be identical too, because the gas is going to expand into that vacuum. No energy is allowed to come in through the walls, and the gas is actually not doing work on anything because it's not pushing anything a distance. It's just kind of expanding out quasi-statically into this vacuum. So not really pushing anything to do work. No work is done by the gas. The system is isolated, no heat is transferred in. Internal energy remains the same. You can see how this is different from the previous example. In the previous example, we had two transfers going on. Heat had to come in while the gas was doing work on something. The final state is the same as this final state, where we have no change in the internal energy and no heat or work done. So energy transfers by heat, like the work done, depend on the initial and final and intermediate states of the system. So work and heat being transfer variables depend on the path that we take. Neither can be determined solely by the endpoints of a thermodynamic process, even though internal energy only depends on your points. And pressure only depends on your points, and volume only depends on your points. But the transfer variables depend on your path. Here's some special processes. We define what we call an adiabatic process. One where no energy is allowed to exchange with the outside. So no heat is allowed to exchange with the outside. No heat from the outside is coming in, and no heat is going out. So it's kind of insulated in terms of heat. One way you can achieve this is by having really good insulation, or you can have your process proceed so quickly that heat doesn't have a chance to be exchanged. So in the case of a piston like this, you either compress it really fast or expand it really fast and not allow the heat exchange to occur. That takes a little bit of time.
So we wouldn't use a system going so quickly that it would allow combustion in a car.
Well, that's exactly what you'd use this for.
But aren't you creating combustion within that piston?
Yes.
So is it just to prevent the engine?
Well, you want the energy created in that combustion process. You want most of it to push the piston down. You don't want it to release as thermal energy. Because if you capture that as mechanical engine, if you capture it as mechanical energy, you're getting better gas mileage, more torque.
That's one of them.
Right?
For instance, let's think about a diesel engine. How does a diesel engine ignite its gas? You have this vaporized gas.
It has a very high compression ratio compared to a gas engine. So as it compresses it heats up the gas so much that when you inject the diesel, it ignites itself without needing a spark plug.
Exactly. No spark plug. So how a diesel engine works is there's actually it happens fast, right? So you compress it fast. By compressing it fast, you're doing work on the gas. So you're adding energy to the gas, but not from heat. You're doing it by mechanical work, by the compression of the cylinder. All right? And hence, the internal energy of the gas goes up, and the temperature goes up. That ignites the gas. And then that will do work in the opposite stroke of the engine.
Diesel engines also usually have to be built out of cast iron or by cast iron sleeves inside the engine. They typically run slower than the gas, and the RPMs are typically slower than the gas because they're so much heavier that if you start running it so fast, you know, that you have a lot of centrifugal.
So, is it
Because the pistons are a lot heavier.
they insulate from the exchange of heat then?
No. So you run it slower because the pistons are a lot heavier than a gas engine piston. So as you move, the faster you move it, there's a lot more. You know, it can rip itself apart. So typically it runs at a slower RPM than a gas.
But you can still get a lot of work done because
It has a lot of torque.
a lot of, because you're moving a heavier piston.
That's why you want diesel on tractors and stuff.
All the international trucks, like the penetrating motors, they'll have it'll be like a 6-cylinder, but they'll have like 100 horsepower, they'll have 600 pounds of torque.
Yeah, you get a lot of torque out of it.
We can probably talk about more on that later. Adiabatic process. Since there's no heat exchange, the change in internal energy is due to the work done on the gas specifically, in either direction, if the work were positive or negative. So work is positive if we compress the gas, hence that would increase the internal energy, and as we said in diesel engine, that would raise the temperature, allow ignition to take place. If the gas expands adiabatically, that would decrease the temperature of the gas. What would that be good for? Maybe the opposite stroke in the diesel engine. But what else would that be good for? If you were to suddenly expand the gas, so the gas is doing work on your piston, hence it's losing internal energy. Right? You're doing it adiabatically, so you don't allow any heat exchange to offset that change. If it loses internal energy, what's going to happen?
Condense.
It's going to cool. It's going to cool. So yeah, what you would have in a condenser, say in a refrigerator or any kind of refrigeration system, it would allow anything that's kind of volatile, that you want to use a volatile substance that will want to take over that area, expand adiabatically, cool down, use that as your cooling system. So examples of adiabatic processes relate to engineering, expansion of hot gases in an internal combustion engine, which will cool those gases. The liquefaction of gases in a cooling system, which you just mentioned by expansion, cooling the gas, and a compression stroke in a diesel engine.
And also one of the reasons that it gets so hot compared to a gas engine is because it compresses a lot farther towards the top than gas. Like the compression ratio is, from the maximum area to its like.
Which would be another reason why you'd want a heavier piston, right? So you can help compress the gas
Right.
to a greater amount. That example where we looked at the gas, it's an insulated gas, and we took away the membrane and allowed the gas to expand. There's a name for that kind of expansion. It's called adiabatic free expansion. Adiabatic because we don't allow any heat exchange from the outside. If that were to happen, and this gas doesn't do any work on a piston, it's just expanding into a vacuum, and there's nothing that's pushing on it, then the work done is zero. And since the heat added is zero and the work done is zero, by the first law, change in internal energy is zero, and the initial and final states are the same as far as internal energy goes. Temperature is the same. So no change in temperature would be expected or adiabatic pre-expansion. Isobaric process. Isobaric is a process in which the pressure is constant. Like I said, iso means same, baric means pressure. Constant pressure. Values of the heat and work are generally both non-zero. Work can be easily calculated because if the pressure is constant, then your work is simply a negative pressure times your change in volume. And if volume doesn't change, then you don't have any work. We're just introducing this. We'll have more. I'll reintroduce this later. All these processes. Isovolumetric, sometimes called isochoric, is one in which there is no change in volume. What implications would that have on the first law in terms of work and heat? No work. All right. So if you have an isovolumetric, no work done, that means your change in internal energy will be strictly due to the heat added to the system by the first law. So energy added to the system kept at constant volume. All the transferred energy remains in the system, causing an increase in the internal energy of the system. I think this process is responsible for the misconception that heat is the same as internal energy. Only in this process would the heat add strictly to internal energy in that sense. But heat is the transfer variable and internal energy is a state variable. Isothermal process, one in which it's done at constant temperature, same temperature. Since there is no change in temperature, there is no change in what?
Oh, wait. Heat.
I'll give you a clue. It's one of those three things in the first law.
It's the internal energy that I get right here.
Internal energy, right? We'll actually show that internal energy is directly related to temperature. So as you change the temperature, internal energy goes up or down, you know. See, you change the temperature. Since there's no change in internal energy, by the first law, the heat added to the system will equal the negative work done on the system. Any energy that enters the system by heat must also leave the system by work. It is done isothermal. It might look something like this on a PV diagram. Here's a PV diagram, and we would say that P times V is a constant, so it's a hyperbola. By the ideal gas law, P times equals nRT, PV equals nRT. So PV is related to the temperature, and we're at a constant temperature, and we'll have they're inversely related. One goes up, the other one goes down, and vice versa. We have a hyperbola for that function. So you can imagine on a PV diagram that you'd have these lines, designated by the blue line here, of constant temperature. And there'd be other blue lines, either above or below that, which would represent other temperatures. Right? They obviously would not cross, so you'd have all these hyperbolas that occur on this PV diagram, all representing constant temperatures. The curve itself is called an isotherm. later. Okay, I'm losing my voice.
What's a quasi?
That's doing that expansion really, really slowly, so that you any change you do is infinitesimal. You allow everything to equilibrate with every little change that you do. So you don't do it quickly and then things change after that. So here's the isothermal expansion of the gas. The gas is allowed to expand at constant temperature. We start at a smaller volume with a higher volume, which means that the gas is doing work, which would represent then negative work done on the gas. Now, since the pressure is changing as the volume changes along this curve, we'd have to integrate the pressure as a function of the volume in order to figure out the work. So we have a negative integration of the pressure change in volume from the initial volume to the final volume. But if we say that the pressure is related to the volume by the ideal gas law, then the ideal gas law, PV equals nRT, P would equal nRT over the volume, T being a constant because we're isotherm, constant temperature. So I can take the constant out of the integral. And now I have that the work done is a negative nRT times the integration of dV, d volume over volume. You've done that integration many times. And you know that that is the natural log, in this case, of the volume, from the initial volume to the final volume. So, for an isothermal process, the work done from initial to final volume is nRT times the natural log, and I flip that fraction there because I incorporated a -1 in there. So it's going to be from the initial volume over the final volume. Only for isothermal process. Since the change in internal energy is 0, because you're at the same temperature, so the energy didn't change, that means that the heat added in an isothermal process is equal to the negative of the work done. So the heat added would just be the negative of this expression up here, which again I've incorporated that negative by flipping the ratio there. So the heat added is going to be nRT natural log final volume over initial volume for isothermal process. So here's a summary for special processes. Adiabatic, no heat exchange. Heat added is 0. Change in internal energy then would just be equal to the work done on the system. Isobaric, constant pressure. Work done is equal to negative constant pressure times change in volume. If there's no change in volume, no work done. You have to use the first law to figure out the change in internal energy, because there could be heat added. Isothermal, constant temperature, which means the change in internal energy must be 0. That means that the heat added is equal to the negative work done, and it's given by the expressions that we just showed on the previous screen. That is your first introduction to PV diagrams. Like I said, it'll just give us, and the first law. It'll help us handle the problems in this chapter, and it also gives us a good introduction to problems that are proceed in the next chapter.